All right. Hi, everybody. Welcome to the last SLAM seminar of this spring semester. And we're delighted to have Dr. Cody Schimming as our speaker today. He is at Johns Hopkins University as a William H. Miller III postdoctoral fellow. And he's studying various aspects of liquid crystal order in synthetic and biological systems here. Previously, he was an undergraduate at University of Pennsylvania and did his PhD at University of Minnesota with Jorge Viñals. And his first postdoctoral position was at the Los Alamos National Laboratory with Cynthia Reichart and Charles Reichart. So today he's going to tell us about dynamical phases of active fluids in complex environments. So Cody, take it away.
Okay, thank you, Dan, and I want to thank the organizers of the SLAM seminar for allowing me to share my work today. So yeah, I'm going to be talking about active fluids in complex environments. And let me first tell you what an active fluid is. This is, loosely speaking, a material where the constituents consume energy at the microscale and move around, and this leads to motion at the macro scale. And there are lots of different examples. So here I've just pulled four that look really cool. And you can see there's a lot of variety here. So active fluids can be biological in nature or synthetic. So on the left, at the top left, these are starfish embryos. On the bottom left, this is a bacterial suspension. While on the right, the top right is Janus particles, and the bottom right are Quincke rollers, which are synthetic systems. They can exist on a variety of length scales. So just these four examples here span 2 to 3 orders of magnitude of length scales. And there's a lot of different phenomena associated with different systems. And so you'll see here, sometimes the phenomena can be kind of ordered, like this sort of chiral crystal that forms, or this flocking behavior, or it can be chaotic or turbulent. And so there's a lot of work that goes into understanding the fundamental phenomena of these systems, but there's also a lot of work that goes into understanding how different environments can change the fundamental behaviors. And that's one of the things that I'm interested in. And so confinement and the environment can change the fundamental behaviors of these systems. And what I mean by the environment here is maybe pretty broad. This can be sort of hard boundaries or walls. It can be changing the thing that the active fluid sits on, so the substrate, or it can even be applying external fields to the system, which can, like a electric or magnetic field, which can change the underlying behavior of the system. And so there are sort of different levels of questions we can ask about this. First of all, we can ask, how do these different things change the fundamental behaviors of individual active systems? But there's a higher level, which is, we can ask, are there any general principles of environmental interactions that may apply to multiple active fluids or multiple types of environments? And the reason why we ask these questions is often for the sort of higher goal of designing functional materials, either for biological or technological purposes. And so what I want to talk about today is work that I've done in the past, computational work in the last sort of year and a half or so, on a couple different types of active fluids and several different ways that we've sort of modeled changes in the environment to these active fluids. So to give an overview of what I'm going to talk about, the first part of the talk I'm going to focus on active fluids called active nematics. This was work done in my previous postdoc at Los Alamos with Cynthia and Charles Reichart. And there we looked at two different scenarios, one where there's embedded obstacles in the active nematics, and another where there's sort of activity patterning or change heterogeneity in the active force distribution. And then I'm going to change gears a bit in the second part of the talk and talk about ongoing work with Brian Camley here at Johns Hopkins on a compressible and isotropic active fluid, where we are looking at the behavior when an anisotropic substrate is added. And so my goal for this talk is to provide a sort of a showcase of results rather than dive deep on any of the details in any of these particular topics. So I'm going to try to keep the details as light as possible. And so if you have questions along the way, please feel free to ask as we go. And so I'm going to start by talking about active nematics. An active nematic, if you don't know, is a fluid that has sort of two components. At least I like to think of it as having two components. The first is local orientational order, where we think of the constituents as sort of rod-like, and they prefer to orient along a direction. Oftentimes we'll use a vector to talk about the directionality, but this vector has head-to-tail symmetry, and we call it a director. The other component to an active nematic is a dipolar active force that each of these constituents exerts on its surroundings. So here I'm showing this force as pushing outward along its long axis. So this is an extensile active force. This is the type of active force I'm going to consider for this talk. It could also go the other way and be contractile. So something really interesting happens is when you put these two components together, you generically get chaotic flow and topological defect proliferation. So topological defects are points in the order which are singular, they can't be defined. And so here's three different examples of three different types of active nematics, all showing this phenomenology. On the left is a microtubule kinesin suspension. In the middle is a bacteria suspension in a liquid crystal, in a nematic liquid crystal. And then on the right is a nematic liquid crystal that is being acoustically actuated. And so you can see the sort of chaotic movement of all of them. And on the left, the black dots are the topological defects, and on the right, the topological defects are labeled. They're harder to see in the middle movie, but they're also there. And one thing I want to say about these topological defects, I'm not going to talk too much about them in this talk, but an important aspect is that the positive defects, so they're sort of like charges where they can be positive and negative. The positive ones are motile, and they're the ones that are mainly generating the flow in these systems, while the negative ones tend to sort of stay still in the system or move around very little. Okay, so I'm a computational physicist. I want to model this system, and in particular, I want a model that has these two aspects of active nematics. So to do that at the continuum level, we have to sort of keep track of two things. Is there a question? Okay, so we have to keep track of two different sort of fields at the continuum level. The first is the tensor order parameter for the nematic, which is has the apolar symmetry baked in and has a magnitude which is non-zero when the system is locally aligned and 0 when the system is locally disordered. And to keep track of the dynamics of this, we have to solve a somewhat ugly somewhat ugly equation here. But the physics of it is just that there's linear advection by the underlying fluid. There's a rotational advection, so when there's gradients in the fluid flow, the little rods might want to rotate. And then there's a thermodynamic force which tries to drive the system to a free energy minimum. And the free energy here is a Landau-de Gennes free energy with a one constant elastic energy, which penalizes spatial variations. Additionally, we have to keep track of this fluid velocity. And so to do that, it's governed by the Stokes equation, which includes a viscous force, a substrate friction, because in 2D, all of these systems have to lie on some substrate. And then importantly, that dipolar active force that I was talking about, which is proportional to the nematic tensor order parameter. And the constant of proportionality is alpha, which is the strength of this force. So if alpha is larger, the forces will be stronger. And then we also assume that the fluid is incompressible. So the divergence of V is 0. So the equations here are kind of messy, but you can put them on a computer and simulate them. And if you just put it with periodic boundary conditions, this is sort of what a simulation will look like. So on the left, I'm showing the tensor order parameter. The color is that magnitude, and the lines are the director. So the little blue dots that are moving around are all the topological defects. And on the right, the color is the vorticity, and the arrows are the fluid velocity. And you can see a bunch of vortices being generated. So the sort of chaotic flow mode is given by these equations. And we typically give this phase a name. We call it active turbulence because it has some similarities to inertial turbulence, although it's not quite the same phase. Now, it looks very chaotic, but it actually has some nice statistical properties that I'll want to compare to in a second. So just to introduce those here, the distribution of direction of velocity directions is isotropic. So you can see here it doesn't pick a particular direction, which makes sense. And also the distribution of vorticity is very close to Gaussian. So here the blue curve is the vorticity distribution for this simulation, and the black dotted line is a perfect Gaussian. So you can see it's very close to that. So I'm going to be using these statistical measures to compare to very soon. So just keep these in mind. So now I mentioned that we want to change the environment of this to change the fundamental behavior. And the first thing that I'm going to look at is what happens when you put hard boundaries in the system. So in general, in nematic systems, boundaries induce topological defects. So here's an experimental example from a microtubule kinesin system. Here you have a circular bounded system, and it generates these two positive topological defects, which tend to rotate around one another in the video. And this is because the sort of total winding number has to be +1, and defects in nematics can be half integer, so they can add up to a half, or they can add up to 1 total. Another experiment which actually really inspired the work I'm about to show did sort of the inverse of this and put these triangular posts embedded in the active nematic. And what the effect of this was to basically have a static negative defect sitting in the active nematic. And here there's no external boundary, so the total topological charge is 0, which means each of these posts has to induce a positive defect in the system. And if you remember, the positive defects are the ones that sort of generate all the flow. So our thinking was, well, maybe we want to study this this system of a periodic lattice of these posts systematically, because we know they're going to generate topological defects, and we might see some interesting flow states. So that's the first thing that I want to tell you about.
Cody, had someone already done the case of circular posts in a regular array?
I don't think so, actually.
Okay, that's interesting, because easier to make, but maybe more boring from an active perspective.
Yeah, because the circular ones are going to generate negative defects, which don't generate flow.
Mm-hmm.
But yeah, I don't think, not for an active nematic. People have looked at circular posts in bacterial suspensions. But yeah.
Okay,
thank you.
thanks.
But yeah, so what we're gonna simulate is this periodic array of these triangular posts, and we're going to enforce that the director is parallel to the posts, which will induce positive topological defects. And so just to show you that this happens, if we simulate this with no activity, so there won't be any flow in the system, after it coarsens, you'll see these little blue dots are all positive topological defects, and there's exactly one positive topological defect for each post in the system. Sometimes, multiple get pinned to one post, which means that other ones don't have any next to them, but there's exactly one for each. And so what we wanted to ask then, if we turn up the activity, what types of flow states will we get as we vary both the activity and the distance, the gap distance between these obstacles. So let me show you, if the gap distance is relatively large, in this case d equals 8, and just a note about the units in the simulations, 1 corresponds to a diameter of a topological defect here. So d equals 8 means about 8 topological defects could fit in between here. So the dynamics of the system are seem to be qualitatively very similar to active turbulence. And when we look at the statistics of the distribution of velocities, we find that it's not quite isotropic anymore. There is some perturbation, but if we take any averages of the velocity, we're still going to essentially get zero. And so I would still say that this simulation is still in active turbulence with maybe some perturbation to it.
Could you say
On the
more
other,
about what you mean by the diameter of a defect?
yeah. So if you notice the little blue dots, sort of, they go from blue to red, and so there's a characteristic size of the
The core
defect.
size.
The defect core size. We've sort of normalized everything so that the core size is 1 in our simulation.
Thanks.
Yep. Yeah, thanks for the question. Okay, so if we decrease the distance between these obstacles, it may be hard to see in the video here, but we get positive topological defects that are now consistently moving to the right through these sort of gates almost. And the velocity directions are also pointing to the left. Sorry, I should have said left. Everything is sort of moving to the left. And if you can't see it from the movies, you can see it in the distribution clearly that the velocity directions collapse onto sort of moving towards the left. And maybe you can see this qualitatively easier from comparing the trajectories of simulated tracer particles. So here I'm going to play them at the same time. On the left, the particles sort of move somewhat randomly, but on the right, the tracer particles are consistently moving towards the left, though sometimes they'll get caught in a vortex before moving to sort of the next array of posts. And so this is why we call this this sort of new phase an active nematic ratchet, because the flows are generally moving to the left, but sometimes there's some variation going from one post to the other. And so a good quantitative order parameter for the system is to measure the average velocity in the x direction. And we can do that and plot. So that's what I'm doing here. The color is the average x direction flow velocity. The x-axis is the activity for a simulation, and the y-axis is the gap distance between obstacles. And so here, more blue means that it's sort of moving faster to the left. And we can sort of plot out a phase diagram. So just some features of this phase diagram is that at low activities, we have low speeds, which makes sense. Maybe more interestingly is that there seemed to be a critical obstacle spacing that we needed. And this is just the fact that you need the gap spacing to be small enough where flows cannot curl back in on themselves to go the opposite direction. And then also we have an optimal obstacle spacing here where the reason for this was actually quite interesting. At large, at least at large activities, what's happening when the gap size gets very small is negative topological defects will sit in between the obstacles and block the positive defects from getting through. And so you have this defect blocking, which lowered the overall speeds. And so that sort of gave us this optimal obstacle spacing, where at this spacing, the positive defects could still get through and generate flows all the way through the system.
Does blocking involve annihilating those defects?
Yes. Yeah.
Okay.
Yeah. So the negative defects would sit there, and then the positive defects would annihilate, and they'd effectively screen each other, and the flows would go to zero for a second, right? for some amount of time. But what I want to emphasize with this system is that you get these sort of unidirectional flows by breaking the symmetry of your system, right? We had these asymmetric obstacles, and we could have set them to go in any direction, and it would have broken the symmetry in the direction we wanted. So an obvious follow-up question is, what happens if the obstacles are symmetric instead of asymmetric? And so if we have symmetric obstacles, we're going to sort of asked this question, but we're going to repeat the same study now with these diamond-shaped obstacles, which respect the symmetry of the lattice. That's what I mean by symmetric here. And again, we're going to vary the activity and the distance between the obstacles. Here, we shouldn't get any uniform or sort of unidirectional flow because there's nothing breaking the symmetry. And indeed, we don't get unidirectional flow. We thought maybe we'd get just active turbulence, but in fact, we get something maybe a bit more interesting, which is the system tends to coarsen to have vortices sitting in each of these sort of circular plaquettes. So it's similar to that experiment that I showed before for the single circle, where you have the vortex with two topological defects sort of rotating around one another at the center. But now you have an array of these vortices. And in this case, all of the vortices are the same sign. So here we call this a ferromagnetic vortex lattice, sort of invoking the language from like an Ising system.
There's a question in the chat asking, is there a way to elicit rightward motion? I think referring to the last, the non-symmetric case.
Yeah, I can show this. Yeah, so basically, if you wanted to move it to the right, you would just flip every single triangle the other direction. So about the y-axis, you just reflect. And you could rotate these in sort of about any angle to get whatever angle you want the flow to go in. As long as you have to, you may have to change the overall lattice that you're using as well, because there's some weird things about the squareness of the boundary condition. But yeah, did that answer the question? Yeah, okay.
Yes.
Okay, so yeah, so here we get a ferromagnetic vortex lattice. On the other hand, if we decrease the distance between obstacles, we still get a vortex lattice, but it will coarsen into a state where the vortices now have opposite signs for their nearest neighbors. And so this will eventually become an antiferromagnetic vortex lattice. And I want to emphasize the only difference between these two simulations is the distance between the obstacles, or the size of the obstacles, which is what we varied. The activity is exactly the same between the two. And so to quantify this, we have to work a little bit harder to find an order parameter. What we did is we measured the average vorticity at the center of each of these sort of circular plaquettes. And this gave us basically an analog spin variable for each point on this lattice. And then we could measure a spin-spin correlation function by summing on all nearest neighbors in the system. So this correlation function is +1 for a perfect ferromagnetic lattice and -1 for a perfect antiferromagnetic lattice. And it could be any value in between -1 and +1, but if it's positive, it indicates ferromagnetic order, and negative indicates antiferromagnetic order. And so we can take time averages of this over our simulations, and that's the color of the dots here, and plot this on a phase diagram like before. Again, the x-axis is the activity, the y-axis is the distance between obstacles. And here we find for low activity, we don't get vortex lattices, we just get essentially either pinned defects or defect hopping. At some critical activity though, and large and small gap distance between obstacles, we find a ferromagnetic vortex lattice. At intermediate distances, we find antiferromagnetic vortex lattice. And then for high activity, we recover active turbulence as we expect. And so just by changing the symmetry of the obstacles, we get a completely different sort of phase diagram here. And before I move on, I want to sort of give some intuition for why you get ferromagnetic versus antiferromagnetic. To spoil it a bit, it comes down to a competition between elastic and active forces in the system. So the way we determined this was by increasing the activity, by doing a single simulation that increases the activity at regular intervals across this phase boundary, and then decreasing the activity back down. We were actually initially looking for some hysteresis, and we found a little bit, but that wasn't actually the interesting thing. The interesting thing was when we computed the elastic energy of the configuration at each time step and compared it to the active energy that's sort of injected into the system at each time step, we found that right around the transition, the active energy actually catches up to the elastic energy. And so it makes up for the higher elastic cost of the antiferromagnetic phase. So here the overlaid colors are red for ferromagnetic and blue for antiferromagnetic. In the antiferromagnetic phase, the active energy is consistently larger than the elastic energy of the configuration. And you might ask why the elastic energy in the antiferromagnetic phase is larger than in the ferromagnetic phase. And it has to do with looking at what the director configuration is doing in these phases. So in the ferromagnetic vortex lattice, well, in both vortex lattices, actually, the director takes a sort of chiral structure because of the chirality of the vortex. And if it's ferromagnetic, the chirality does not change. And so the director does not need to change as it goes across one of these boundaries. And so it has a smaller cost of elastic energy. Right? On the other hand, in the antiferromagnetic phase, the chirality has to change, and it would like to do it abruptly. So it's going to cost energy to do that. But luckily, what the active force tends to do is nucleate pairs of topological defects. And these negative defects that sit in the middle are nucleated by the active forces and mediate this change in chirality. And so the active forces can make up for the elastic cost.
There's a question of whether there are any dissipative forces.
There are dissipative forces in the Stokes equation. So there's a viscous force and a substrate friction. Though in this simulation, the substrate friction is very small compared to the viscous force. There's sort of an effective substrate friction because we use no-slip boundary conditions. And so that gives you kind of like an effective screening length because of the no-slip conditions. The vortices can only get that big. Does that answer the question?
Apparently, yes. And I also wanted to make sure I understood. So the matching between neighboring domains here would not be an issue for the elastic energy if you had a tangentially aligned +1 defect in the center, right? It's only because you have some sort of spiral component to each.
Yeah, that's right. That's
Okay.
right. Yep. Yeah.
And do you ever see +1 defects without this kind of ordering?
Where you don't have either ferromagnetic or antiferromagnetic.
Right.
Yeah. So especially in like the regions that we called active turbulence, sometimes you would get sort of long-lasting positive defects. They would eventually sort of pull apart and sort of rearrange. To determine whether or not the state was in active turbulence, we actually didn't use the spin-spin correlation. We used other measures like the number of defects that were being generated or the statistical properties of the flow. But you can get still sort of somewhat stable positive defects in that phase that eventually will go away. But in the vortex lattice phase, they're much more stable. Okay, so yeah, so hopefully I was able to show that you can sort of change the behavior of the system by having some symmetry or asymmetry in your boundaries. I want to move on now to talk about activity patterning. So forget about obstacles in the active nematic. Now we're going to pattern the active forces. And we were inspired to look at this problem by recent experiments that used light-sensitive motor proteins in these microtubule kinesin systems. And so just to show you the experimental image, if the researchers shine light in the bottom corner, they can make it much more active than the rest of the system, and sort of spatiotemporally pattern the activity. And we were interested in asking the question, how does this affect the overall phase behavior? Can you still get active turbulence even if you have sort of a heterogeneous activity? And to answer this question, what we did to try to systematically get to it was to use these activity pattern motifs, where we either looked at a lattice of active circles or a sort of linear array of active stripes. So here the color is the activity. Do you have a question?
Nope, I pressed that button by accident.
Okay.
Right.
So the color is the activity. So the tan regions are highly active, and the black regions have no activity. And the whole point of the study was to vary the maximum activity as well as the length scales for the patterning. So either the distance between the circles or the distance between the stripes. And so let me show you what we found for the circles first. It turns out that if the circles are far away from one another, we just get localized dynamics. And what I mean by this is that the positive defects tended to stay only in the active regions, and vortices were generated only in active regions. You can sort of see it in the stills here. Now, it turns out that you can transition back to active turbulence, to full system active turbulence, by increasing the activity density. And you can get active turbulence before you get to homogeneously distributed activity. And so just to show you here, the topological defects are sort of zipping all over the place now. And you can see in the still here that vortices are being generated sort of agnostic to the distribution of the activity. Now, what we thought would happen from here is that if we increase the activity, we would still be in active turbulence, because typically when you increase the activity, all you do is create more topological defects or increase speeds. But it turns out for this system, if we kept the activity, the sort of lattice constant the same, but increase the maximum activity, we would go back to the localized dynamic state. And so you can see it even better here. Now, again, we get these states where you have these tightly bound positive topological defects and an individual vortex for each circle. And to get back to active turbulence, we had to increase the activity density even further before we could get to the state where there are vortices generated everywhere. And so it turns out that at higher activities, you actually need to be closer to homogeneous activity, which is sort of counterintuitive to us, at least at the start. And so I've been calling these systems, these states, active turbulence. Let me sort of justify that by showing you the vorticity distribution. So these are the two vorticity distributions for the states that I was calling active turbulence. Again, the dashed black line here is a perfect Gaussian. So they're very close to perfect Gaussians. On the other hand, the vorticity distributions for the localized dynamics have these really long-tailed distributions. And the long-tailed are understood because the vortices are only being generated in the active regions. They're not being generated in the inactive regions. And so you get a sharper peak at 0. Luckily for us, there is a statistical measure of the tailedness of a distribution called the excess kurtosis, which is just the ratio of the fourth central moment to the variance of the distribution. And if you subtract 3 from this, it's 0 for a perfect Gaussian. This measure has been used in previous studies of active nematics, and even in studies of inertial turbulence for high Reynolds number fluids as well. But the upshot is that we get a single number that we can measure for every simulation, and again, plot a nice phase diagram. So here the color is the log of the excess kurtosis, just because this gets really large for high values. So you can see the features a lot better if we plot the log. And here the y-axis now is the maximum activity in the system, and the x-axis is the distance between active circles. And so if I rearrange this data and show you where each of these distributions come from, you can see that this white line demarcates a sort of phase transition, where on the left we have active turbulence, right? These Gaussian distributions versus localized dynamics. So this was for the activity circles. It turns out for the activity stripe system, we found a very similar transition, which was not obvious to us at the start that we would find a similar transition. So if the stripes are well separated, we also get sort of localized dynamics. Here, the movies are going to look a little bit more active, but that's because there's an entire one-dimensional degree of freedom where everything can move around in. But the vortices are still mostly being generated only in the active regions, and the positive defects are staying in their lane. They're not moving from one to the other. At some point, if we move the stripes closer together, we do recover full system active turbulence, where now the topological defects are exploring all of space, and the vortices are being generated in the inactive regions and in the active regions, just sort of all over. And again, we can quantify this with the distributions of vorticity. On one side, we get something very close to Gaussian. On the other, we have something with long tails. And so we can plot again, the excess kurtosis and find a transition between 2D active turbulence and localized dynamics. Sometimes we would call this state actually 1D active turbulence because the system looked like sort of individual channels rather than a full two-dimensional system, but it's a localized system. To give you some intuition for why this transition is occurring, it actually is just an interplay of length scales in the system. And it has to do with something that I haven't introduced yet. It's this active length scale, which is set by the competition of elastic and active forces. Essentially, it's proportional to 1 over the square root of the activity. And if you replot those transition curves that I just showed, where now the y-axis is the critical active length scale instead of the critical activity, for both the circles and the stripes, the critical active length scale just goes linearly with the distance between the active regions. And so we have this sort of rule of thumb where if the active length scale is much larger than the patterning length scale, you should expect to have full system active turbulence. In this regime, you don't have to worry about the patterning shape. On the other hand, if the active length scale is much smaller than this patterning length, then you should expect localized dynamics. And then your dynamics might depend on how you pattern the activity. So there's one more thing I want to show about the activity patterning, and that is, you may have noticed for the stripes, it may have looked like I was only showing half of a phase diagram, and indeed I was. So the full phase diagram looks like this. We actually found a second phase transition in the system. So for really high activities, we found that the system would coarsen into a system where you have very stable vortices and, again, positive defects that tightly wind around one another. So similar to the vortex lattices, but now they're sort of confined to these activity stripes. And if you watch as many simulations as I do, you start to see maybe there's a pattern here where you have sort of anti-ferromagnetic ordering along the y-axis, and maybe there's some ferromagnetic ordering or a tendency to ferromagnetically order along the x-axis. Actually, it can be kind of cool. Sometimes they'll sort of slide into place over much longer timescales. But of course, we can make this quantitative by measuring a spin-spin correlation function, similar to the vortex lattice, except now we're measuring this sort of only along the x-axis or only along the y-axis. And for this particular simulation, over time, along the x-axis, it does tend to go positive. And over time, along the y-axis, it does tend to go negative. In fact, at long times, it tends to be very close to perfectly antiferromagnetic. But what what I find really interesting is actually we can understand this from the explanation I gave from the vortex ordering before, right? Along the x-axis, what's coupling these vortices? Well, this is an inactive active nematic coupling them, so it's only elastic forces that are coupling them, right? So along the x direction, it's coupled by elastic forces, and that leads to ferromagnetic ordering. Along the y-axis, it's dominated by active forces, and we know that leads to antiferromagnetic ordering. And so it was nice to be able to take some of the intuition we got for the vortex lattice system and apply it to this system, and I think it still holds.
There are two questions in the chat. One of them asks, have you considered the inverse of the circle case, where you block light within the circles and illuminate everywhere else? And further, from the circle and stripes experiments, do you have any data about the total area of illumination, and whether that is important along with the particular pattern?
Yeah. Okay, these are good questions. So the first question was, do we consider the inverse? So that has actually already been considered. There's a paper, I think it was published in Soft Matter by Holger Stark's group, where they looked at essentially that inverse problem, where you illuminated everything except for, I think they did a square lattice of circles, and they found a whole phase diagram of various sort of behaviors. And then the second question was about the essentially how the density depends on, or how it depends on the density of activity, right?
Right.
Yeah, so there is a one-to-one, at least for, well, for both of these systems. Maybe I can go back a bit. So there is a one-to-one correspondence from the sort of lattice constant to the activity density, and actually the activity density is the thing we wanted to really is the thing that we varied systematically. So we varied the density systematically and then converted it to these length scales, because once we realized it was an interplay of length scales that was going on, we wanted to write things in terms of length scales rather than the density. So you can go between the two of them. I do think an interesting follow-up sort of study would be, instead of having this sort of nice lattice of circles, to just randomly generate circles at a specific density and see if you get a similar transition. I don't know exactly what that would look like. And that's how we started to do this. But then we realized we need way more simulations than I had time to do. So we used the more ordered case because you don't need as many simulations to look at it systematically. But hopefully that answers the question.
Yes, Jocelyn says, thank you so much. That's a cool follow-up to consider. There's also a question, are the activity heterogeneity and patterning emergent and therefore not deterministic, i.e. impose positive and negative defects?
So the experiments that inspired us were the light sensitive microtubule experiments where they do impose the activity heterogeneity. But I while I was working on this, I was considering the case that even if you're not explicitly patterning activity, you are going to have some distribution of your activity. Like the ATP is not going to be uniformly distributed and things like this. And I think some of this analysis can also sort of apply to that case. And in fact, we're showing that, if your active length scale is larger than sort of the heterogeneity length scale, you don't have to worry about the fact that it is heterogeneous, right? Does that make sense? I don't know if that answered the question.
Yeah, maybe in case it was a clarification question, these are illumination patterns that the experimentalists impose with a certain choice, and
Yeah,
then the rest of the dynamics is emergent. But the circles here are imagined to be a choice by the
yeah,
experimenter.
yeah. Oh, sorry, yeah. The essentially the way we do these is in the equation for alpha, we write that as a function of space, um, rather than just have it as a constant.
Okay.
Okay, let me jump to. Okay, so I'm gonna move on from active pneumatics now in the last 10 to 15 minutes, and talk about ongoing work that, again, I'm doing with Brian Camley here on a compressible isotropic active fluid. And first I want to give you sort of some experimental motivation for why we started thinking about this. And it had to do with cellular tissue on anisotropic substrates. And in particular, how does substrate anisotropy affect the behavior of cellular sheets? So often, cells, especially the type of cells which are naturally elongated, are thought of as active pneumatics. And so one of the things that researchers do is they'll sort of put them on different patterns to sort of um, uh, have the cells take on certain nematic patterns themselves. So there was a study that was done very recently where the researchers patterned positive topological defects with ridges in the substrate. And all of these were positive defects. What they changed was the angle of the ridges with respect to the radial direction. So for theta not equals 0, you get this sort of diverging pattern. For theta not equals pi/2, you get the concentric circles. And anywhere in between, you get this sort of spiral pattern. And what they found, here's a movie from their experiment. These are sort of the fluorescence of the cells over time. They found for all of the angles, regardless of what they chose, the cells tended to accumulate at the center. And just to show you as an average, this is the density as a function of distance from the center. And in fact, they were able to determine that the cells were actually moving over time towards the center. And so this is the radial velocity, the average radial velocity as a function of distance of the cells as well. And so if you want to describe cells as active pneumatics, at least using the model that I showed at the first part of the talk, you would actually predict that theta naught equals 0 and pi/2 would give you the opposite behavior. You would not see sort of the same qualitative behavior for both of those. So you have two options. One is to modify your active pneumatic theory, or your other is to try to model this as some other type of system. And so that's sort of what we were motivated by in studying this this model. So let me tell you the model, and then maybe, hopefully, you might see why we were thinking of it for the system. The model comes from Bois, Juluker, and Grill from a paper from 2011. And it's essentially a model for an isotropic compressible active fluid. So here you keep track of just a density field, which obeys mass conservation. The mass conservation just has advection by the underlying fluid and diffusion via Fick's law. And then the fluid velocity, just like before, obeys the Stokes equation with some substrate friction. And the stress here now has a viscous stress. It also has a compressive stress because it's a compressible active fluid, and then an active stress like before. But now the active stress is a function of the density, not of any sort of ordering. There's no order to this fluid. It's an isotropic fluid, so it's only a function of the density. And you can think of this active stress as sort of like a contractile active stress in the sense that you think of all of the particles in the fluid pulling on each other. If there's a higher, if all the particles are pulling on each other, the higher density region is going to win out on average, and so the active force is going to point towards the higher density region. So that's what this is essentially modeling.
But
And
so are we thinking about time scales of cell migration rather than cell division here?
yes, yeah.
Okay.
Yeah, we are not worrying about the proliferation of the cells in the
Okay.
model, at least with as far as we've gotten with the model. So, um, but yeah, so this model has actually been used in several biological contexts to model different things. It has been used to model tissue dynamics in a different type of cellular tissue. It's been used to model cytoskeletal actin dynamics, and it's also been used to model sort of generic activator inhibitor systems. A slightly more complicated version of the model has been used to do that. And so, why has it been used to do these? Well, the fundamental behavior of this model is that it has a phase transition to what is sort of called a pattern-forming fluid. So let me describe that. If the activity, still given by alpha here, is less than some critical value, diffusion wins out, and you just have a homogeneous system. However, if the activity is larger than some critical value, you get regions of large density that become stable. So here's a simulation in 2 dimensions. The color is the density field, and the lines here are now the velocity field of the fluid. Again, it's a compressible fluid, so there can be divergences in the velocity. But what you get is this sort of stable clump of stuff, right? And it's pretty easy to understand the physics of this. This is just a balance of advection and diffusion. You have this active stress, which is generating flows, and then you have diffusion trying to spread everything out. So it's the balance of these that sets the sort of size of this cluster. All right, and so this is why we were thinking that at least some of the physics might be involved in the cellular system. Except we need one more component, which is sort of an anisotropic substrate. So how can we model anisotropic friction? Well, if we have this spiral case, we can pick a point and decompose that point into a parallel and perpendicular axis. And these parallel and perpendicular axes can change in space. But once we do that, we can say that the frictional force is just given by a coefficient of friction that is greater in the perpendicular direction than in the parallel direction. And this has the effect of modifying the Stokes equation just in the term for the friction, where now this is a matrix that depends on space. Everything else is the same. You just have this friction coefficient that's now a matrix. And so for the spiral case, you can find these axes by, again, you have some angle with respect to the radial direction, and so you can write down the parallel axis in terms of this angle and the radial and azimuthal directions, which also change in space. And so let me show you what happens when we simulate this. We get, for all cases that I'm showing here, we get accumulation at the center. So again, the color is the density field. I've overlaid sort of what the ridge pattern might look like for these theta knots. And we get central accumulation. And so that's qualitatively similar to the experiment. We are still trying to figure out how much we want to quantitatively compare it to the experiment. There are some differences, but there's also one other caveat that we're sort of cheating here. And that's because we set the initial condition to have a small bump at the center. And this allows it to accumulate at the center. Now we are sort of cheating, although we're inspired by the experiments, and their earliest time data looks just like this initial condition where there's a small bump at the center. But we wanted to check that this also holds if we sort of randomize the initialization. So we no longer have a bump at the center. What we find if the initialization is randomized, so I'll go through them one by one. For theta naught equals 0, you might have the clump sort of nucleate far away, but it will eventually go towards the center. All the way up to theta naught equals pi over 4, we will generically find that the sort of cluster will accumulate at the center. However, above theta naught equals pi over 4, we found that this is not guaranteed. And so if the cluster sort of nucleates away from the center, we get a state where the cluster will sort of circle around, and it'll just keep circling around forever. So you get this sort of dynamical state where it won't stay still because of the anisotropic friction. In the other extreme of theta naught equals pi over 2, if the cluster does not form at the center, it will just get pushed away. And here it's moving actually because of the periodic boundary conditions. It's just picking the sort of y direction because that's where it nucleated closest to. But if I increase the system size, it would sort of sit just far away from where it nucleated. And so what's going on here? How can we understand this? We have to make a couple approximations, but then we can sort of write down an intuitive model. So first, let's think of the cluster as just this sort of circular Gaussian. If we think of it like this, then the active force that's generated is just pointing everywhere towards the center. And if we add to this anisotropy, so here I'm thinking of theta naught equals 0 and pi over 2, sort of along the x-axis far from the center. If we overlay our cluster on this anisotropy pattern, you'll see for theta naught equals 0, the active force is more parallel to the anisotropy on the right side than on the left side, which means that the forces pointing inward on the right side will be larger, and we should expect a velocity that goes towards the center. The same analysis applies for theta naught equals pi over 2, but here it's exactly the opposite, right? On the left side, the active force is commensurate with the anisotropy, and so we'll get an overall motion outward. And this applies for all the angles in between 0 and pi over 2. You just sort of continuously swing this arrow from inward to outward. And that's why if it's not at 0 or pi over 2, you can find this circular motion, right? And so we have a simple intuitive model for this. The last thing I want to show is maybe a way we can use this to get linear directed motion for this model. Oh, and I should mention, like, I'm not sure if this happens in the experiments at all. I've not seen that reported. So we're unsure whether or not you could actually do this in the cellular system. But we think it's interesting that you can get this motion from a model that actually doesn't have any motion in its fundamental behavior, right? Just from changing the boundaries. And so we wanted to play with that a little bit and use this principle to sort of design a friction pattern for directed motion. And sort of the simplest thing we came up with is this sort of V-shaped friction pattern, where now, again, if you overlay the cluster on it, you should have a larger active force in the back than in the front and predict motion going downwards. And when we simulate it, of course, we get this directed motion, which will go here. The boundaries are periodic, so it'll just keep going forever and ever. So I just want to sort of, at a high level, remind you that this is happening because there's some asymmetry. It's this asymmetry that's leading to overall motion. And if you remember all the way back to the first project that I talked about, which was these asymmetric obstacles in the active nematic, that also led to this sort of directed motion. So there is a bit of a connection between asymmetry and motion in these active systems. And I know that's something that's often used in non-equilibrium systems in general to generate motion. Okay, so that's all I wanted to talk about today. I'll leave you with a few conclusions. The first is I've shown several examples of how complex environments can alter the behavior of fluids. One of the things that seem to be important is the symmetry versus the asymmetry of the environment and how that can make a pretty big difference in the types of emergent behaviors. So the asymmetry, as we've seen, tends to lead to sort of directed motion, or at least on average, whereas symmetry tends to lead to more ordered behaviors. And with respect to this last project that we're still working on, one thing I want to emphasize is that the internal structure of an active fluid, for example, nematic ordering or something like that, is actually not necessary to induce motion if there's some structure in the environment. So I think it's just as important to ask, what is the environment of this fluid it's just as important to ask that as it is to ask what is the overall structure. So I'll leave you with that, and I'm happy to take your questions and thank you, and just leave you with a video that I made for the conclusion where I made these sort of railroad tracks for the cluster. So thank you.
All right. Thank you for a wonderful talk. So we'll open it up to questions, and I'll start by reading out the one question that appeared in the chat in the past couple of minutes, which is, or actually, Muhung, you're welcome to unmute and read the question yourself since we're now in the open Q&A section. If not, then I'll just, oh, it doesn't have a mic. Okay. I wonder if there's obvious reasons why the cluster seems more elongated for the cases where theta is greater than pi/4.
Yeah. So that's something. So I assume you meant in this situation. So something like this, the cluster is a bit elongated here. That has to do with the fact that it's similar to what I was saying about the active force before. It's just feeling sort of a different amount of anisotropy on its ends than it is on its sides, and so it'll sort of compress. Something we looked at too is if you just have a uniform anisotropic case, you can actually get sort of elongated clusters as well, rather than circular clusters, just because of the distribution of anisotropy over the sort of boundary of the cluster, if that makes sense.
Okay. They say, I see, thank you. All right, other questions? Feel free to unmute.
I have a question. Can you hear me?
Yep.
Yes.
Yeah, so my mic is working. I have a question about the ferromagnetic order. You mentioned that it was favorable because it's taking a lot of active energy, but why does that make it favorable? Is it the case of maximum entropy production?
Yeah, so I think there's a couple reasons probably why it's favorable. For one, let me see if I can go back to that slide. Why the active energy favors antiferromagnetic? For one, it's inducing topological defects, and these topological defects need to sit somewhere. And so it actually, if these topological defects have to exist, it's minimizing the elastic energy for them to sit perfectly in the middle, and they will mediate this change. The other mechanism probably that's happening is that it's favorable for the sort of viscous forces in the fluid flow term to have opposite chirality in the fluid flow, because then there are smaller shear forces or smaller shear terms, smaller shear in between these. So it's probably multiple reasons, but those are two that I've thought of.
Thank you, and thank you for the talk.
Yeah, of course.
All right, another question typed in the chat. Pennate diatoms look like components of an active fluid, but individually often change directions. Have you looked at this case? And I had a related question, which is the cells tend to do this reversals of the one-dimensional motion, and is that part of the model, or should it be?
Okay, so it's asking if about cell reversals. So that is not explicitly modeled. So again, the model that we're using is sort of the simplest possible thing you could write down, where there's no structure in the fluid. So I think in order to model, if you wanted to explicitly model like reversals in the system, you would have to have either some sort of polar ordering or nematic ordering in the model, at least at the continuum level. So here, if that is going on, we're sort of coarse graining that out with the model, if that makes sense. So it's not explicitly included in the model. It could be another mechanism for what's going on in the experiment, certainly. Hopefully that was helpful.
Yeah. I think so. I mean, I agree with your statement that it is remarkable how far you get without thinking about really the mechanism of activity.
Right.
Yeah, and I'm wondering if the opposite sign of eta tilde, coming back to the idea of proliferation, is that something you're also thinking about?
Yeah, so I mean, obviously the easiest way to introduce proliferation to this model is to just make this
Uh,
non-zero and depend on
right,
the concentration.
right.
That is something I haven't done yet, and I mean I can very easily do it in the simulations, but we still have a lot of data to look at where there's no proliferation.
Gotcha.
But it has been looked at sort of in some of these other studies where
Mm.
this side is non-zero. The model we're using here is actually simpler than some of these other studies.
All right. Any further questions? Oh, oh wait. Oh no, I scrolled wrong. Okay, looks like not at the moment. So please join me in thanking Dr. Schimming again for a wonderful talk. And please look out for news of the next SLAM seminar in coming months.